Hey guys, this video is going to be about counting big numbers of things. For example, how many different ways could you make a lottery numbers, or how many different telephone numbers are possible in the United States, how many different license plates could possibly be made, how many different passwords could you possibly create for your cell phone, or how many different possible ones could you make for a lock of some sort. That had numbers or letters for inputs. So that's kind of what we're going to be talking about. So we're going to start with this math dude who is going to talk about how many outfits he can make to wear on his show. He's got 3 pairs of pants, blue, khaki, and black. He's got 5 t-shirts, red, blue, yellow, green, and purple, and then 4 kind of button-up or polo type shirts to go over his t-shirt. He's got yellow, black, green, and blue. So how many different outfits could he make for the show? And trying to count up how many different outfits he could make might be a little bit difficult. That's a lot of outfits. Were you able to count how many there were? So one way we could try to help figure out how many outfits he can make is to make a tree diagram. So for pants, he has 3 options: blue and khaki and black. I'm going to zoom out so we can see this a little bit better and then add on the t-shirts. So he's got 5 colors of t-shirts for each pair of pants. He's got red, blue, yellow, green, and purple, and then we need to list that out for each one of the different pairs of pants. And then for each of those t-shirts, we've got 4 of those other shirts that are going to go over the top. And so we've got yellow, black, green, and blue for those, and we need to put one of those on every one of the t-shirts. So that gives us all of these possibilities. And I'm not going to try and draw all of those out there, but you can kind of see what's happening here. We'd have all of these down here, and then that would show us how many different outfits that he could make. But drawing that all out is kind of a pain, and we can kind of see what to do anyway. We can see we have 3 pairs of pants, and for each of those 3 we have 5 t-shirts. So that's like 3 times 5, and that gives us the number of pants and t-shirt options. And then for each one of those options, we have another option with the shirt on top. When there's 4 of those, so we can times that by 4, and that gives us all of the options: 3 times 5 times 4, 60 different outfits that he can make. Let's look at an example of a student who goes to a school that just has 6 class periods, and he's decided already which 6 classes he wants to take: English, physics, government, pre-calculus, Spanish, and journalism. And he wants to know how many different schedules are possible. We're going to assume that every class is offered every hour to start with. So he's got all of these choices. This is what we call a decision chart, where we're looking at, he's got 6 different class periods. He has a choice for each class period, so he has 6 different decisions to make. So he has 6 choices for first hour. That's our first decision. Once he's made that decision, that class is here. It has to be here. So he doesn't have 6 choices left for second hour. He only has 5 choices left. And third hour, fourth hour, and only 1 choice left once he's picked first through fifth. Only 1 choice left for sixth hour. And so we just multiply those together. This is like having a big tree diagram with all 6 choices for first hour, and then each of those choices has the other 5 coming out of it for second hour. And so it makes this big thing that we wouldn't want to draw out, but we can figure it out just by multiplying these together. And so 6 times 5 times 4 times 3 times 2 times 1, that is 720 different class options when you multiply all of those together. Well, what if pre-calculus is only offered first hour? What if he can't take pre-calculus any other time? Then we need a new decision chart. He only has 1 choice for first hour if he wants to take pre-calculus, and it's only offered first hour. But then he still has 5 choices left for second hour, everything but pre-calculus. Then once he picks a class for there, 4, 3, 2, and 1. So 1 times 5 times 4 times 3 times 2 times 1. So it just changes a little bit when we add some of these different things in. And that gives us 120 different class choices if pre-calculus is only offered first hour. These types of situations show up quite often where you end up just starting at one integer and moving down one integer until you get to 1 when you're multiplying together. The same thing happened here. 1 times, that wouldn't matter if that weren't there. It would still be the same. 5 times 4 times 3 times 2 times 1. We start at an integer and work down, multiplying all of the integers all the way down to 1 together. And so this has a special name called factorial. Another way of doing this is to just do 6 factorial, and we write factorial with an exclamation mark symbol. So 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, which equals 720. So this one would be 1 times 5 factorial, and again, 1 times anything is just that thing, so just 5 factorial, which is 120. So that factorial button comes in really handy on your calculator. Let me show you where that is. On these ones that we've been using in class, it's right here in this PRB for probability. It has these other choices right here, which we'll learn about later, and then this one right here. So I have to type in the number first, 6 factorial 720, or 5 factorial 120. So depending on what type of calculator you've got that you're using, hopefully you can find where its factorial button is, or you can always just look up a calculator online that uses factorials and use that. You can do these by hand. You don't need a calculator to do them, but it is sometimes easier with a calculator. You can just type it out by hand. It takes a little bit longer. And I'll even show you in a minute some ways to do some of these a little bit faster by hand when you have multiple factorials in the same problem. But we will be doing some things a little bit later on that we're going to learn about in this lesson that have some other buttons that are useful to have. So if you don't have a calculator that does those, or you can't find one online or other place that you can use, you are welcome to come to the school and check out a calculator. You'll just need to get in contact with your teacher about when you're coming so that we can have one ready for you. So we're just looking at an example of some factorials combined together. 9 factorial divided by 6 factorial. So 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You don't want to go clear to 0, because if you times it by 0, it'll just be 0. You always stop at 1, and then divided by 6 times 4 times 3 times 2 times 1. Each of these just divides to 1, and we're left with 9 times 8 times 7. And so 9 times 8 times 7 is 504. Another way that we could do this same problem, 9 factorial divided by 6 factorial, is 9 times 8 times 7 times 6 factorial divided by 6 factorial. So 6 factorial divided by 6 factorial is just 1, and we're left with the same thing. 9 times 8 times 7 equals 504. So here's another one, 7 factorial divided by 4 factorial times 3 factorial on the bottom. Again, we can just write it clear out, and all of the 4 times 3 times 2 times 1 just divide to be 1. And then we have 3 times 2, which is the same as 6, so those can divide out with the 6, and we're just left with 7 times 5, which is 35 over 1, which we don't have to write. Let's just try one more. 20 factorial divided by 18 factorial times 2 factorial. So 20 times 19 times 18 factorial, I don't want to write that clear out, and then divided by 18 factorial, which those reduce to 1. And so we just have 20 times 19 over 2 times 1. 20 divided by 2 is 10, so we're left with 10 times 19, which is 190, and then divided by 1 is just still 190. So that is the fundamental counting principle and how factorials work. Basically, it just says that if we have 2 independent events, then we can multiply the number of outcomes for each to get the number of outcomes for both. All right, so now we're going to talk about permutations. We're going to start by looking at an example. So let's look at the case where you're just trying to come up with a 4-digit passcode. So we have a 4-digit passcode, 10 choices for the first digit, 10 choices for the second, 10 choices for the third, and 10 choices for the fourth. All the digits 0 through 9 for each one of these 4-digit passcode. So that gives us a total of 10,000 possible passcodes. Another way of writing that is like 10 to the 4th power, right? So what if there was a stipulation or a change to that your digits couldn't repeat? If you used 5 for your first digit, then you couldn't use 5 for any of the other digits. That would change this just a little bit. We still have 4 digits. We still have 4 things that we're coming up with. We have 10 choices for the first, But once we've made that decision, we have one less choice. And once we've made that, one less choice. And once we've made that, one less choice. So that's 10 times 9 times 8 times 7. It looks kind of like a factorial, but it's not quite the same because we stopped at 7. We didn't go all the way down to 1. And so it's just a little bit different. And this is what is called a permutation. That gives us 5,040 options when we multiply those together. So in a permutation, you are trying to arrange things or do things in a way where they cannot repeat. And the order matters. If you're making a passcode or a password, and you had like a password of 5479, that's different than 9745. That's different than 9457. Those are all different. So the order of the numbers matters. If you put them in the wrong order, it's still not going to unlock. So that's what makes a permutation, where we're not repeating and where the order matters. Okay, so let's look at one other example of a permutation where order matters. Let's say some people are running in a race and that there are, let's say, 50 people running this race, and they are wanting to figure out how many different ways first, second, and third place could be handed out. So we've got first place in the race, second place in the race, and third place in the race. So there are 50 people who could possibly come in first place, assuming that they're all equally likely to win, I guess. Once someone comes in first, there's only 49 people left who could come in second, and only 48 people left who could come in third. So 50 times 49 times 48, and so we've got 117,600 different ways these 50 people could finish in first, second, and third place. So we can kind of see this pattern here that we could maybe write a formula to help us. It's, again, kind of like factorial, but we're missing a lot of it. So this really is the same as 50 factorial divided by 47 factorial. Everything from 47 down reduces to 1, and we're just left with 50 times 49 times 48. So the way that we can kind of come up with a formula for this is we have to think about where the 47 came from. The 47 came from, we started with 50 people and we assigned 3 of them spots, and then we didn't worry about anyone else. So that's really coming from 50 factorial divided by 50 minus 3 factorial. 50 is the number we had to start with. We had 50 people. We use n to represent that. And then we're going to do a permutation. We used a capital P for that. And then we have R different things. R is the letter that we use to represent how many different places we're putting those things in. So we have n permutation R. And so we have our formula here, n factorial divided by n minus r factorial. So let's see if that works now when we go back up to this example right here with the passcode or the password that needed to not have repeated digits. So we had 10 digits to choose from. So we have n factorial 10. And then we're picking 4 of them to be in our password or our passcode. So this would be 10 minus 4. That's how we would put that into our permutation. So that's just 10 factorial divided by 6 factorial, which is 10 times 9 times 8 times 7. And then the 6 factorial from the top and the 6 factorial from the bottom reduced to 1. And we're left with exactly what we had before, the 5,040 options. So the great thing about, again, the calculators that can do this is it does the permutation for you. So what you have to do, let's do this one we just talked about, the 10P4. You want to type in the 10 first, and then go to that probability button. Again, it's right here on this type of calculator. Sometimes it's in a math menu and then over to probability. It just depends on the calculator you're using. So you hit probability, and it's right there, that first choice. NPR says we're doing a permutation. See how it looks just like what we had here in our equation. I can find it there again. There we go. NPR, NPR. So 10, and then we're picking 4 of them. So 5,040. So that is how you do your permutation. So again, a permutation is an arrangement where the order matters and items cannot be repeated. We can do that using that NPR. N is the number of items, and R is the number that we're selecting that we're going to be arranging. So the last way to count that we're going to talk about is what's called a combination. It's very much like a permutation, but the order does not matter. It still has a set number of things and they cannot repeat, but the order does not matter. So one way I kind of like to try and think about this is that a permutation is kind of like a presidency. Say we have 3 people in a presidency, a president, a vice president, and a secretary. Where a combination is more like a committee. We just have a 3-member committee. There's no specific positions. So let's say we have like Al and Betty and Carl in this presidency versus having Al and Betty and Carl in this committee. If we trade them around a little bit here, now Betty is the president, where Al used to be the president. This is a different presidency, this line, than this one. But if we trade them around in the committee, they're all still in the committee. It's still the same 3 people in the committee. And so this does not count as a different committee, where it does count as a different presidency. So if we have these 3 people coming into our presidency or into our committee, we can see that we have a lot more choices with permutations than we do with combinations. In fact, when you look at all of the different presidencies we could make with A, B, and C here, Al, Betty, and Carl, it turns out that any of the 3 could be the president. There's 2 left then to choose for the vice president, and 1 left to choose for the secretary. So that's 3 factorial different options we have here that we don't have over here. So when we're looking for a formula for combinations, it's the same as we would do with permutations, except that we have to divide out all of these because we don't want them to all count as separate. They're all one thing there, which happens to be R, or the number of spots or things that we're selecting, factorial. So for a combination, this is our formula, n factorial divided by n minus r factorial, and also divided by r factorial. So an example of a combination would be something, say for example, I have 20 things and I want to put 4 of them in my backpack. So it doesn't really matter what order they're in there, I just want them to be in my backpack. I can't choose one of them more than once because I have 20 different things, and so I'm going to pick each one once, so I actually have 4 items in my backpack. So that would be like 20 combination 4. So using our formula, it would look like this. Again, your calculator can do this. It's in the same spot as the permutations and the factorial are. Hopefully you can find a calculator again that can do that for you. So I'm just going to type in 20, go find my combination, and 4. And so that tells me there are 4,845 different ways I could do that. I also want to look at the difference here if it had been a permutation. Say I was taking 20 books and arranging them on a shelf. So there was 4 books lined up next to each other on the shelf. A certain book being here looks different than if that book is over here. And so if I did that 20 permutation 4, you can see I have a lot more options. 116,280 is a lot more than 4,845, which is the difference between doing a permutation where the order does matter and a combination where the order does not matter. So just to summarize, a combination is where we are selecting some things, there are no repeats allowed, and the order does not matter. This also talks about 0 factorial, which equals 1, and you can read through this, pause this and read through it if you want to know more about why 0 factorial equals 1. Now let's look at how we decide which of our different counting methods to use. We're going to use this flow chart to help us out. So the first question you want to ask yourself is repetition allowed? If repetition is not allowed, then it'll be a permutation or combination. We'll come back to that. But if repetition is allowed, then we're going to be looking at, does the order matter? If the order does matter, then we're looking at those types of problems where we just have our decision chart, how many choices for each, and if we're just looking at a set number of things and picking so many of them, it turns into what we did with that 10 times 10 times 10 times 10 for the passcode where we could repeat, which is n to the r power. If, on the other hand, order does not matter, then we have to look at sub-cases and consider some different parts and then put all of those together, which gets a lot more complicated. So now let's look at when repetition is not allowed. Again, looking at does order matter? Yes. Then it is a permutation. Does order matter? If the answer is no, then it's a combination. And we can use our formulas to help us with those types of problems. So now we're going to just look at an example of where we could use these different cases. So let's say that you're going to go into an ice cream shop and you are going to get 3 scoops of ice cream. You have 2 choices. You can get those 3 scoops on an ice cream cone, or you can get them in a bowl. And let's also say that your friend has maybe challenged you or something to get 3 different flavors. You can't get all of your same flavor. So let's look at those 2 scenarios and decide which they are. We'll start off with 3 different flavors on a cone, and then we'll do 3 different flavors in a dish. We decided to go with our friend's challenge and not repeat. So repetition is not allowed. And then we're looking at does order matter. If we say order does matter, we're going to be getting an ice cream cone. The cone has 3 different spots. It has a bottom scoop, a middle scoop, and a top scoop. And so that's going to look different. We're going to eat it in a different order. Whereas if we have it in a dish, it's all in there together. We can take bites of whatever we want, whenever, multiple flavors at the same time, whatever we want. That's where order does not matter. We're going to pretend now that this ice cream shop only has 5 flavors just to make the numbers smaller and easier to work with. So they've got 5 flavors. We are choosing 3 of them. We're taking 3 different flavors and we're stacking them in an order on our cone. So that is a permutation. And so that gives us 60 different ice cream cone options. Now we're going to take a look at the dish situation. Again, there's 5 flavors of ice cream here. And the order did matter with the cone, but it doesn't matter with the dish. There's not a top, a middle, and a bottom. So it's a combination, 5 flavors. We're picking to eat 3 scoops. We're getting a 3 scoop thing here. And so we don't have as many dish options as we had with ice cream cones where the order mattered. When the order doesn't matter, we have a lot less options. We have 10 different dishes of ice cream we can get. So now let's take away that idea that maybe we're going to get 3 different flavors. Maybe we want all 3 to be the same. We want to just look at all of the possibilities. How many total possibilities there if we are allowed to repeat? Maybe get 2 the same and 1 different. How many different ice cream cones and then how many different dishes are available to us in this new scenario? All right, let's look now at repetition is allowed. We don't know whether we're going to repeat or not, but we might. And so if we look at that and then look at does order matter, we'll start with order does matter. So again, that is the ice cream cone. We've got a top, we've got a middle, we've got a bottom. We're probably going to eat them in that order. So the order does matter. So we're going to look at these 3 different scoops, top, middle, and bottom, and look at how many choices we have for each. Again, this ice cream shop only has 5 flavors of ice cream, and so our top scoop we have 5 choices. For our middle scoop, we can choose to use the same flavor or a different flavor. It doesn't really matter. So we still have 5 choices. And then lastly, our bottom scoop, again, we're deciding. So 5 choices. So that's what we were talking about before. We've got 5 different options, and we're choosing 3 of them. That ends up being 5 to the 3rd power. 5 times 5 times 5 is 5 to the 3rd power, which gives us 125 different ice cream cones we can make, which you can see is a lot bigger if we're saying we can repeat. We get way more cones than if we didn't repeat, which was our permutation from before. Now let's look at this harder situation where we do not have an order and we are allowed to repeat. A dish with 3 scoops of ice cream. So in this one, we do have to look at different sub-cases. We've got some different options here. We could choose, out of the 5 flavors of ice cream, we could choose to have 3 flavors. All 3 scoops a different flavor. And that would be kind of what we looked at before with the combinations. There's 10 different ways to do that. Instead of choosing 3 different flavors, we could choose 2 different flavors. But when we choose 2 different flavors, we could do it in different ways. Pretend we're using chocolate and vanilla. We could do 2 chocolate and 1 vanilla, or we could do 2 vanilla and 1 chocolate. It's still only choosing 2 flavors, but there's 2 ways within that choice to figure out 2 flavors. And so we have to take that into consideration. We can do 2 and 1 one way, or 1 and 2 the other way. And so 5 choices of ice cream, we're going to pick 2 of those flavors. And so when we do that, there's 2 ways to do it once we've chosen the 2 flavors. And so we have to do 2 times 5, choose 2. And it's the same whether we're looking at it in a line like this, or if you look at it the way it would be in the dish. 2 chocolate, 1 vanilla looks different than 2 vanilla, 1 chocolate. You can see there's a different number of scoops. Whereas when we had the 3 different scoops, it's 1 of each. There's not a different way to do it. Our last option is to just choose 1 flavor. Choose all 3 scoops in our bowl to be a different, all the same flavor. No difference. All 3 are the same. Doesn't matter how you rearrange those in the bowl. They're looking the same. There's not 2 and 1 or 1 and 2 kind of a situation like we had there. So we just have the option of the 3 flavors, 2 times the options with 2 flavors, and then the option with 1 flavor. And so when we add all of these together, that gives us the total number of dishes when we do repeat is 35 dishes of ice cream. And that's it. That is how we can do counting using the fundamental counting principle, using combinations, permutations, and kind of different combinations of each of those. So good luck. That's our last topic that we're going to be learning about, that we're going to have our last mastery check on. So please, again, let us know if you have any questions, if you need any help. And that is the last thing that we're going to be learning.